All right.
Apologize.
All right, so everybody knows each other. Wait, which one is this? Oh, wrong one. There we go. There we go. All right, we all know each other. We're just missing Jesse, I guess, but we'll charge through. Coming to you today from the dining room. Nothing like Zoom. You guys will see every room in my house at some point. Hopefully the squirrels are kind to me outdoors. My dogs don't go crazy. But anyway, so let's get going with today. So yesterday, we looked at the whys of radiation. What is it, right? Where does it come from? Where can we find it? These kinds of things. Today, we're going to look at the biological effects of it, because that, to me, at least, is always more fascinating than the whys. And we kind of did the same thing with properties, chemical and physical properties of hazardous materials. We looked at some chemistry stuff, and then we did, toxicology stuff about why this stuff harms us. So now we're going to look at the biological effects of this stuff. So same thing as before, these learning objectives come right out of the Department of Energy's requirements. So going through this module, you'll be able to, pass the RAD Worker 1 and 2 biological effects of radiation test if you were ever to take it. But at the end of this module, we'll be able to identify major sources of natural background and man-made radiation and the average annual dose of each received by the general population, state how radiation causes damage to cells, identify the possible effects of radiation on cells, define acute and chronic dose, and state examples of chronic radiation. And some of these terms are going to probably be familiar because they kind of mimic or are exactly like stuff that we learned from toxicology or the chemical side. Define terms somatic and heritable effects, state potential effects associated with prenatal radiation dose, and compare biological risk to the general population from chronic radiation dose and the risk to workers who are subjected to radiation in their daily work. And I'm going to give you a couple versions of slides for this number 7. One of them is going to be what the DOE wants to hear. So, they've been saying for a long time, we don't really have any real data that shows that, workers who work as radiation workers have increased health effects or cancers at the levels that we have them work around. But that's just not true. There's, recent research that within the past 5 years that shows absolutely not true. And I'm going to cover that too. Again, it's getting this, very large federal agency to change how it's been doing something. It's been very difficult. And it's easy. I admit I'm wrong every day, both to my wife and my kids, right? And, as a good scientist, if we learn that there's a different direction we need to go based on data, we need to do that. And that's not really happening yet in the DOE. It is happening, though, in other countries, similar agencies like France, in the UK, things like that. But we'll cover that as we get to that slide. So just a quick review from yesterday. One of the take homes I just want us all to remember is that radiation can extend out from its source. So radiation, how would you folks describe radiation after what we learned yesterday?
Almost like a cloud of dust that just spreads.
Yeah. Yeah. So instead of cloud, is there another term that we used over and over again yesterday?
Wave?
Yeah, wave. Exactly. It's a wave. Another way that we can think of it is it's energy in motion. So it's energy that's not just staying put. It's reaching out. Like if you throw a pebble into a pond or something like that. And there's a couple ways, though, that we can be affected as far as our health is concerned. One is we can get a dose from that wave, right? Or that photon, if we consider radiation to be a particle and wave together, as we talked about yesterday. So we can be away from a radiological source and get hit by that wave. What's the other way that we can be affected by a radiological source that we talked about yesterday?
So contact, direct
Yeah,
contamination?
right, exactly. So it's kind of a double whammy. We don't have to be near it, depending upon the source, because remember back when I said alpha radiation, as long as you're, a couple inches away, you're not going to be affected by it unless it's floating around in the air and it happens to get on your skin or you breathe it in. We also mentioned that skin is a good barrier against alpha radiation, but if you breathe it in, if it contacts your eyes, that's a different story. So that's troubling because it's got two ways of harming us. It can harm us from a distance, depending upon what the source is, or it can harm us up close if we get contaminated, especially if we get internally contaminated with radiation. That's a real kicker right there if we get internally contaminated. I mentioned this yesterday. So this is, and I'm gonna botch this because I don't speak Portuguese. Guiana, Brazil. It's near Sao Paulo.
Goiânia.
Goiânia. I don't know if I was close. Usually I try to run through words I don't know, like with a sounding checker. I forgot to do it. I think it's near Sao Paulo in Rio de Janeiro, Brazil. And this was an incident that was well documented. It was studied not just on the Brazilian government's level, but also internationally. And it's a great example of how contamination can spread. So what happened was there was a cesium-137. I think yesterday I said it was a cobalt source, but it was cesium-137. And it was inside this thing up here in the top right corner. It was in a dental X-ray device. And it was broken open and it was glowing. And they, these two folks thought it was really cool. The intensity of the source was 1,375 curies, which is very strong. And I'm going to compare that to some biological damage later on in the module. So we'll get back to this number, but this is a really high source. Cesium-137 has a radiological half-life of 30 years. So after 30 years, half of those radiological cesium-137 atoms turn into something else. The biological half-life, which is different, is the time it takes for that chemical in your body for half of that to be eliminated. That is 70 days. So the combination of a fairly long, for our human existence, right? 30 years is a long time. Half-life of 30 years and the biological elimination rate to get out of our body of 70 days, which is pretty long. This is troubling if this were to get inside of us. So what happened was they brought this back and showed folks in their town, showed their friends and family, tried to sell it. And what ended up happening were they had to go, and by they I mean the internet, I think it was the International Radiological Protection Group, and also the authorities in Brazil that are responsible for radiation protection. They did have to call in international help to do this. They evaluated 112,000 different people, because that's the number of people that they assumed could have come in contact with this contamination. What they found was from this evaluation, 249 people were actually contaminated. And of them, 129 had internal contamination. So, about more than half actually had this stuff inside their body. The other folks that were contaminated just had external contamination, so they could remove it. It was on their clothes, their skin. Of this 129, 50 had to be medically monitored because they had high enough internal contamination dose rates coming out of their body that was concerning, and 4 people died. And on top of that, the whole kind of area of effect was 29 square miles. So I think San Francisco is 7 square miles or 9 square miles, if memory serves. So imagine that. Imagine 29 square miles. That's how far this found source traveled before it was caught, right? So it caused quite a bit of havoc. So, and this is a concern for us in case we get into, say, the Homeland Security kind of protection stuff, where if we look at a dirty bomb, where these things can be made with low-level radiological materials, and it's not necessarily an issue of it, killing or injuring somebody immediately by radiation, It's the fact that it's going to be very difficult to clean up, that contamination can spread over a large area, make an area, for the most part, unusable. Um, so it shows how contamination can spread if it's not controlled. That's why, just like with chemical stuff, it's always best if we can prevent exposure to workers from the get-go. All right, so the first objective that we have here: identify the major sources of natural background and man-made radiation and the average annual dose of each received by the general population. So now we're going to look at where this stuff comes from. And towards the end of the module, what we're going to do is we're going to do an activity where we actually get to calculate our own average annual dose. There's a worksheet that we have in the manual that we're going to go through together. And it's fairly accurate. So who can state some sources of radiation? So in general, where do you think radiation comes from?
We talked about radon yesterday, right?
Yep. Okay. Yeah. So radon.
Stuff in the medical field like X-rays,
Yep.
CAT scans, stuff like that.
Yep. Stuff. Yep. Absolutely. Any other things we mentioned?
The sun.
Yep. The sun. Absolutely.
Something as simple as your microwave at home could generate
Yeah.
some radiation.
Exactly. Yep. And you're going to see, so one of the places on that dose calculation sheet is if you look at video terminal screens like TVs, computer screens and stuff, you have to add a numerical value because that increases your total radiation dose. What does that look like in the time of the pandemic? Since I think we're probably all on our computer screens, I don't know, probably 10 times more than we're used to. So it might be a little different for the last year.
And I'm going to venture out and say that microwave is going to be running a little more than usual as well.
Yes, it is. It is. So here's some general places. We've got cosmic radiation, like, from the sun that you mentioned, also all that, cosmic dust and stuff that we get bombarded through our atmosphere. Terrestrial, so forms inside the Earth's crust, stuff we put in our body. Medical, you mentioned, some consumer products. Other types, so this would be things like, radiological waste, stuff we might use, in the building and construction trades, research, things like that. Radon was mentioned, right? So the average dose in the US from all these sources together is about 360 millirem. So 1,000 millirem equals 1 rem. And the Department of Energy allowable dose for a worker in 1 year is 5 rem. So this is about almost about 100 times less than what the Department of Energy dose is for a worker that's allowed in 1 year. So the two main categories are natural and man-made. We're going to look at these categories a little closer here. So the natural sources are consisting of cosmic radiation, terrestrial, internal sources, and radon. And this is the bulk of what we get as far as an absorbed dose of radiation into our body every year. It's about 296 millirem each year. So you can see that most of it comes from this. The other, sources like the man-made sources, your X-rays, all that other stuff, that accounts for a very small amount. So cosmic radiation comes from outer space, our own sun. The amount that we receive depends where we live. So if you live closer to sea level, you're going to get less cosmic radiation than if you live higher. And also if you live in some different parts of the world. Does anybody know the reason why? Why would you get less if you live closer to sea level? It's also not great if you live in Australia.
Is it just that you're closer to the sun?
Yep, that's you could say that's one of the reasons, but what is it? What kind of protection do we lose as we get closer to the sun? That ozone layer, right? We have this thick layer of gases, dust, vapors, right? That's in our atmosphere. And that helps weed out a lot of this cosmic radiation. But as you get closer to the sun, you get farther away from sea level. So if you live in, Colorado, some really high places like that, you have less of a barrier between you and those cosmic, forms of radiation coming. Also, the ozone layer, which ozone is not good for us if we get exposed to it. It's very harmful, but it's really good at getting rid of some of these UV A, B, and C rays from the sun. So places like Australia, if you look, we have an ozone hole, which has actually gotten a little better over the last 10 years. But nonetheless, it's a hole in our ozone. And because of the weather pattern, how, the atmosphere circles around Australia, every now and then this hole kind of passes by the continent of Australia. So they have a fairly high incidence of skin cancer for, a large population compared to other places in the world. So that ozone layer in our atmosphere, does a good job at filtering out some of this stuff. And the average annual dose is about 28 milligram a year. Terrestrial radiation, these are sources that are found in the earth. Average dose in the US is 28 milligram per year. So this is separate from radon, and we'll cover radon in a little bit. But granite is a great example. So, I've got granite blocks, rocks in my yard. They are radioactive, not strong enough for me to pick it up with a Geiger counter, but if I were to send it to a lab to have those radionuclides, radiological material counted, they'd be able to detect it. So there are some, forms in the earth that are radioactive because that's what is happening. We showed that decay chain of uranium-238 yesterday. And there's, like I said, a dozen or so decay chains, and they're all at different levels. And some of those decay chains have different atoms. Some are radioactive, some are not. And that's just found naturally in the earth. Internal sources are what we would find in food and water and what we take into us. So, I mentioned salt yesterday. Sodium-24 is one of those isotopes that's not stable. It's a very small component, though, of our table salt. Carbon-14 is a isotope of regular carbon. Argon, and then potassium-40, I mentioned the bananas, right? We'd have to eat 40,000 bananas in a very, very quick time to reach that Department of Energy annual dose limit of 5 rem a year. This here is a photo of Brazil nuts. So you can actually take, a huge bag of Brazil nuts and paste it up and concentrate that stuff. And you can get some, readings with a Geiger counter, although you'd have to eat, pounds and pounds of these things very quickly to have any biological damage result. And the benefits of eating Brazil nuts far outweigh the damage of the small amount of radiation that's in them. But nonetheless, some of our food does have this stuff. The average dose is 40 milligram a year. Here's some examples of foods that have radioactive isotopes in them. So I've got potassium-40, and this is picocuries per kilogram of material or food. Picocurie is very, 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 very small. It's even smaller than micro. And then I've also got radium-226 over here. And again, it's in picocuries per kilogram of food. Bananas is fairly high. Brazil nuts, I mentioned. Beer. So depending upon, what kind of beer you like to drink, some of that material that they use to brew beer might have some radiological isotopes in them. Red meats, lima beans, which is a shame because these are really healthy for you, but nonetheless, you'd have to eat pounds and pounds and pounds of these things to have a negative effect. But it's around us, right? And this does add to our accumulated dose every year. Now we get to radon, the silent killer, and no joke. So radon-222 comes from the decay of uranium. And this is something you don't have to be a radiological worker or be concerned about working around radiation. This is a public health issue. So, something like this, I don't know if you're teaching, basic like chemical awareness or safety, this is something that we could all do for our members as a public good if you just clip a couple of these slides and put it in that training, whatever it is you're doing, because it's going to, maybe prevent some folks from having a home that has high levels of radon. So it comes from the radioactive decay of uranium, and I showed you, that decay chain yesterday. It's about halfway down. Radon gas can emit through the soil and into air. So we call it a gas, but it's more like that photon. So it's a particle. Radon is an alpha particle, so it's an alpha emitter. And the way that it can get to us, if I'm walking around outside and I have high levels of radon in the ground, I'm not too concerned. But in my home, that's different. So this stuff is going to seep up through the cracks. I don't know if I can draw this right. Show you an example of this. Expand my view here for a minute. So it's not going to work. Oh, it did. It did. Damn it. Prop issues. Can folks see this?
Yes.
And you thought I just like comics and MMA? No, I'm an artist as well. So this is an example of our footing of a house, and you see the little key there in the middle, right? And then going vertically, we've got a wall, and then horizontally, we poured our floor, right? So you can see those three pieces intersect. So air likes to follow the path of least resistance. So you're going to have air infiltrate from beneath your home into your basement just through that, even if it's poured right and it's nice and tight. It just happens. So it's very difficult to separate the air from under your house and the air in your basement, and then hence the rest of your house, because that air is eventually going to work its way up to your first floor, your second floor. So that's if it's done right. But let's say if you've got cracks, right? Or if you've got a sump pump where you've got a hole cut in your floor, right? To get water out, things like that. These are all spots for radon to seep into your home or your workplace. And if that happens, you might be developing appreciable amounts of radon that can damage our lungs. And you're not going to know it's there unless you test. And one of the issues is that a lot of builders and real estate agents don't know about radon. It's getting better, but 15 years ago, I thought about, my wife and I were going to build a home, and it was right before the home crash. And luckily we were able to walk away from that, and we bought a already made home. But when I was helping design it, I said, look, I want, I think I asked for like an 80 mil vapor barrier to be put down on top of the crushed stone before they poured the floor. And the builder's like, why? I said, because I don't want, I want to try to prevent as much radon as I can from getting into my home. I live in New Hampshire. He's like, what's radon? And so I talked to him about it. And then I, talked to my real estate agent. And the real estate agent said, oh, Bernie, you don't need to know about radon. We don't have to worry about it up here. It's not that big of a deal. And he didn't know what I did for a living. So instead of me talking, I just sent them the link to the EPA radon page. Very quickly after, I got emails back both from the builder and the real estate agent. Oh my God, do you think we're going to be sued by all of our clients because we told them that this stuff's not harmless? It's not true. This stuff is very harmless. It's also very easy to correct for if you do have it. So
Hey, Bernie,
yeah.
just on that. So like, for example, here in New Jersey, if you buy a home, and I'm sure it's the same everywhere else, when you go through your inspections, they do the radon inspection as well. Is this something that we should do on a regular basis? Because obviously it came back negative, everything was good, but I guess there's always a possibility that those levels will build up, correct?
So Nuno, that is an excellent question. And it's not necessarily that they would change much. You'd have to have either like a new crack in the foundation or something if you had enough radon beneath your basement to begin with. But my question is this: do you believe that they took a representative sample in your house? And by that I mean this: my old house, when we were selling it, the inspector came and he did his radon tests, and I watched him set up the little, and they just took a sampler from Home Depot, which you can do. It's not the best way to do it. I'd actually have, an accredited lab come out and do it. But I watched him put the sampler out, and he put it up near the window. And I said, why are you doing that? He's like, well, I'm just putting the radon, sample collection device up here. I said, that's not where you want to put it, man. I said, you're putting it up near the window where there's a draft in my basement. I said, what do the directions say? And he reads the directions that say you should put it, within 2 feet of the floor in the center of the basement. Make sure all your doors and windows are shut for at least 48 hours before the test. And that's the right way to do it, because if you don't want to find radon, fine, put your detection, your collection, canister up by the window and open the window. So if you can remember, how did they take that sample? If you're comfortable with that, then don't redo it. If you have a question, then redo it. I mean, just using the Home Depot one, is fine enough for a quick summation of what's going on. So what you'd want to do is you'd want to, retest. It's a good idea to retest it in the winter, because air doesn't move as much in the winter. It's not as hot, and so it's not going to move around as much. And typically we have less air filtration in our homes naturally, because we don't open up doors and windows as much in the winter. So what you want to do is develop a worst case scenario. So make sure all your windows and your doors are shut for at least 48 hours and put it in the middle of your basement. And I would put it, 6 inches off the floor, maybe a foot off the floor, and test it
Yeah,
that
so
way.
so yeah, mine was actually done in December. Was right before we closed, and it was probably about a good 4 or 5 feet off the ground, because it was on a ledge on the wall
Mhm.
that comes from the upstairs down to the basement. But yeah, everything had been closed, and I remember they were going to send that sample out to a lab. I'm
Yeah.
not sure if it was a Home Depot piece or not, but that's how they went about it. But yeah, now that you're talking about it, I should probably get it retested just
Yeah.
for
So,
peace of mind.
the Home Depot kits, those get sent back out to an accredited lab, but whoever's taking your sample, who knows if they're really qualified to do it. Um, so with that said, we'll go through and look at some more of this. The average dose, you can see it's the largest amount. So I said that we had like an average of 300 and was it 40 or 60 milligram a year total. This makes up the bulk of it, folks with potential radon. So, how it happens is, again, you've got uranium deposits deep in the earth. It's decaying. This stuff percolates up through the soil, and it's going to get into buildings. And it's not just a home that I would worry about. I mean, if you're working in an office building, 8 hours a day, if you're a firefighter, I would want to have that environment tested, because that's 8 hours a day. And like we said yesterday, some fire rotations are 24 hours at a time. Maybe they're 12-hour shifts. So you're in there for a long time, kind of like a second home. Um, so it's going to infiltrate from all these places. It also, if you've got well water, things like that, it's going to, come in through your well water as well. So I had to have my air tested, and I also had my water tested. And I'll share my results in a moment. So we can see here, this is the EPA map of radon zones. Zone 1 means you typically can find more than 4 picocuries per liter of air. And that is the cutoff where EPA recommends. There's no requirement to do this, but it's a recommendation. It's the best practice. If you've got 4 picocuries or more, put in a mitigation system, which there's a bunch of easy ways to do this. You could simply, real cheap Bernie Missoula industrial hygiene way of doing it on clearance, mind you. You could just cut a small 4-inch hole, in your slab, stick a 4-inch pipe in there, run it out, and then put a very, very low RPM fan on there, which hardly uses any energy, and just keep that thing turning really gentle. You don't want to have it spin too fast. You just want to have it spin nice and gentle. And what's going to happen is that thing, just like if you put a straw in a cake pan or a pie plate, right? You're only sucking from one little area in that thing, but you're going to, draw all the water towards that straw. Same thing will happen with radon gas. It's all going to go to that pipe. It's going to go out your home, up out that pipe outside, and render it harmless. So that's the real cheap way of doing it. But you can spend 5,000 plus on a fancy radon mitigation system. The best way to handle it, though, is when you're building a house. You put stuff in place ahead of time. The easiest way, besides that vapor barrier I mentioned before, is you just put perforated pipes. You put a couple of them on the ground, you run them out, and then you run a stack up outside of the house, and just by passive, displacement of higher concentrations of air with radon to the outdoors, it removes it. That's the best way to do it up front. Moving on here. If you're in zone 2, which I am in, I live right about here, 2 to 4 picocuries per liter. My indoor basement air is 1.2. That's when I had it tested, and that's with me shutting everything up. Now, even during the winter, though, I have the windows open and I have a walkout garage, so I can open those doors. When I do that, I get a good air exchange. It's not at the level where I would do something yet. If it was closer to 2, I would put in a passive system. And then if you're in zone 3, it's less than 2. Now, don't take this as certainty. You might live in one of these red sections and you might have lucked out. You might have gotten no uranium deposits beneath you. A good example, one of my mentors, Dr. Rob Palermo, ended up, in his later years, his kids went to college, so they downgraded and moved to a condo out near Hampton Beach. And it was a condo unit. And so they had, I don't know how many units were in here, but he had really high levels of radon and he had to put in an aftermarket system. The very next unit that was attached to his unit did not have high levels of radon. We're only talking a distance of 20 feet, where the measurements were taken. If you look at the inside of his basement to the inside of the basement of the next unit. So you really have to do your own test. But if I see somewhere that's red and orange, I would want to make sure I'm doing a test, whether it's a home that I'm in now and I haven't tested before, or I'm going to be purchasing a new home. So again, it's important to do something like this because, chronic radon exposure is deadly. It's the second leading cause of lung cancer after smoking. So, we look at some deaths per year here from a couple of, exposures. Radon, 21,000, drunk driving, it's almost double. Falls in a home, drownings, home fires. So it's a very high fatality rate from radon. Any comments or questions? And just to drive it home, so I'm gonna try this. This is an EPA did like a contest to try to create a public service announcement around a case study for radon, and this here was the winning video. So let's see if this works. Are folks seeing YouTube come up?
Not yet.
Not yet, no.
Not yet. Okay, let's see. I'll have to do it this way then. So it came up by hitting the link, but it didn't let me. Can you see it now?
Oh, there it is.
Can you guys see that?
Yeah, I see
Yes.
it.
Okay. My technical abilities never cease. All right, now I just got to figure out how to play it again.
Volume's really low.
Bernie, we can't hear it, so you might want to pause it. Let's see.
Any ideas, Nicole?
Is your
We're fine.
volume all the way up on your YouTube, and is the volume up on your speakers?
Yeah, put the volume up on my speakers. Let's see YouTube. Yeah, volume's all the way up. So I'll try it again from beginning.
We're getting zero sound.
Still no sound.
Bernie, you hear us?
Yeah.
Look, no sound for us still for some reason. It's
Ah.
totally silent. I don't know why. It probably has to do with the Zoom thing. I don't know what's up with it though.
Oh man. Oh well. Well, I take it back about my technical expertise.
Hey, Bernie, can you copy that link from your thing, stick it in the chat, and then everybody should be able to just play it real quick.
Yeah,
It's only a minute long, so if we
Yeah.
see it, and then we can sort of do it that way.
good idea.
Maybe it's worth a shot. There is a trick, but I can't, on a spot like this, remember what the trick is.
Okay, so I guess take a couple minutes, watch that, and then come on back. Serious public health thing, you know, and it's not like it's advertised well, right? You know, and in fact, the only reason why I found this EPA video is because I was actively looking to put together something to, you know, train folks on radiation health effects. And it's not like this came across my news feed or anything like that. Back in 2008, I had to actively search for it. Realistically, what would be reasonable is if, you know, home building associations got training on this, real estate agents, et cetera. But yeah, so, you know, don't just look at your home, but look at, you know, your place of work. And in fact, you know, when I have done, you know, health risk assessments, including radiological dose assessments for the United Steelworkers for their worker protection program, I was doing the risk assessments for Dr. Lou Pepper at Queens College, I think, or Hunter College. And, you know, one of the things that we had to look at was radon for folks who worked at, you know, these Department of Energy sites, like the Stafford Linear Accelerator, which is this radiation using research device, which happens to be located underground in rock. So, you know, we had to look at, well, what's their health risk just from walking in the door, never mind using the, you know, the linear accelerator. So just something to think about. Moving on from that, you know, very uplifting video. The 4 top man-made radiological resources are tobacco products, medical uses, building materials, and domestic water supply. So again, I had to test like my, you know, my basement air for radon, and then I also had to test my water. And you know, again, it comes down to who's doing the test. So if you have somebody who doesn't know what they're doing or is shady and turns your faucet on because you have a well, and they only let it run for 30 seconds and collect the sample, they would not be getting the water from deep down in the well, which has the most radon. You know, so you're supposed to run the water for at least 10 minutes. You know, I would run it for 20. And that's how you would take a representative sample. So let's look at these things. The average dose, again, rounds out the natural sources. So this is 64 millirem a year. You can see it's a minor contribution to the total amount. Tobacco products, as we know, these things are not good for us in any way, shape, or form. And unfortunately, the company saw fit to make it addictive. These things contain radium, polonium-210, and lead-210. So all these things are radiological sources, and when they're in your body, they don't leave your body very easily. Each one of these things has a biological half-life, so a time it takes for half of that to leave your body, and as well as a radiological half-life for a time it takes for half that material, atoms, to degrade into something different. Average dose from smokers, so this is something to know, through tobacco use is 1,300 millirem a year. So this is, you know, a third of the Department of Energy annual dose for a radiation worker. Medical uses, a couple of folks mentioned, you know, these before. So we've got a couple different types. We've got computed tomography, about 150 millirem a year. Nuclear medicine, so those agents that they might put into the body to try to either destroy, you know, harmful cancer-causing cells, and they kill our good cells too. Also like radio dyes, tracers, things like that. And then radiography and fluoroscopy, it's about 75 millirem a year. The average dose is about 300 millirem. The newer systems, like the newer CAT scan, the newer MRIs, they actually have a smaller dose of radiation, which is a good thing. Building materials, so mainly bricks, concrete, and stone are containing of radiological material. So, if this is your trade, if you work with this stuff every day, you're likely to have a little bit higher radiation dose on average annually than folks who don't work with those materials. It's not going to be a lot, but it will, would be noticeable if you were taking biological, samples. Wood can also contain radioactive atoms. The average dose is about 7 millirem a year.
Hey, Bernie, what about glass?
No, I haven't seen anything for glass. Good question, though. It's made of sand, right? But no.
Okay, thanks.
You're welcome. This is an example. So, wood, it's basically built like a giant straw, right? It sucks up water and nutrients and stuff. In fact, we use certain plants to help remediate hazardous waste that's in the ground, because the plants do a great job sucking, stuff up. Doesn't work for everything, but sometimes that's one of the remediation controls. So this is an example in Italy where they had to call 10,000 tons of radioactive wood pellets. Happened back in 2009. So this isn't something that happened in the 70s or 60s. They had cesium-137, and once burned, it creates an ash. I've got 2 pellet stoves myself, and that ash is going to potentially be able to expose the users or the occupants of the home. Especially when I clean the stove, there's a little bit of ash that comes out, and I can tell because it's there's a little layer of dust on my mantle and on the floor and stuff like that. It accumulates there. So stuff can find its way into wood. And then the other place I mentioned was water. This is more of an issue if you have got well water, not necessarily public supply. Although, like we learned from the Flint water case, right, where they just started taking the raw water out of the Flint, Michigan, and depending upon, I guess I should say that, depending upon where your municipal water comes from. And we see the dose is about 5 millirem a year. I mentioned this case study yesterday, where we had the fallout from the Chernobyl reactor going critical. It contaminated the surrounding area. So when there are wildfires there, this stuff gets kicked back up and it exposes and contaminates the wildland firefighters. This is just a summary, so we can see radon accounts for 55% of the total annual dose that we've got from radiological materials. Next in we've got cosmic and terrestrial, about 8%, internal sources. So our food, water, about 11%. And then we can see some of the other things that are the man-made products that make up the rest of our dose. Any comments or questions? All right, let's keep rolling here. So let's see how radiation damages cells. So what's the way that we learn about effects of ionizing radiation on humans?
So it knocks the electron off to alter the atom in your cells.
Good. So yeah, so that's how it causes the damage. But how did we figure that out? You're right, Steve. But what are the 2 avenues that we've learned about that?
Testing on animals, for example? Or
Yep, testing on animals, that's one. And what's the other one? Unfortunately.
Autopsies?
Yeah,
People.
Reports and
People.
Yeah, people who've been exposed. So
Yes, exactly. So unfortunately, right? So we're the guinea pigs. I should probably have a worker next to this guinea pig. Man, that sucks. Even today, it still works out that way, where workers are the guinea pigs. So there's 4 major groups that we've studied. Now, so I'm going to show you the slides that the DOE would want me to show, but I'm going to talk about what the real stuff is behind the slides. So there's 4 major groups of people that have been affected by radiation, and that's where we get most of our current models, at least that are used in the United States. So early radiation workers, so these are folks that worked at the Hanfords and the Savannah Rivers and those places, Los Alamos, who did the early work to develop the radiological fuel. The survivors of the 2 nuclear bombs that were dropped in Japan, radiation accident victims, and then medical patients. Now the problem is all these here are very high radiation dose events. These aren't really people, you know, these early radiation workers. Remember how I said that health physicists came on the scene after they started seeing sickness and illness from the people working and developing this stuff? So these were kind of uncontrolled radiological exposures. They didn't have stuff in place like we did after the 1950s. So for the most part, all these things are very high dose rate exposures to radiological materials. And so what they did is they said, okay, well, they have these high dose rates. This is what happened. And so they just drew this graph that's linear. So it goes from 0 up basically. And so what they're saying is, you know, the more you get, you're going to double your health effects. That's not true. We've got a lot of research today that shows that it's not necessarily linear, and that you can have health effects from very low chronic levels of radiation, the kind that our current radiation workers get. And I'm going to share that research with you in just a moment. It's not easy to discuss. The Department of Energy does not like to talk about this. I represented as an expert Local 598, the plumbers and steam fitters out at Hanford, Washington, because there were 2 recent incidents where their members, along with other trades union workers out there, got exposed and contaminated, including internal contamination to radiation materials, including plutonium. And the DOE was trying to say, oh, don't worry about it. It's you know, the levels that you have are okay, but they're saying that based on old data and old research. And so I was bringing up the new data and the new research, and the response that I got, or I should say the response that the local union got was, well, we have that and we are in the process of evaluating it. So that was a way to be non-responsive to what to what we were bringing up. So just take this with a grain of salt. Another very recent significant disaster was Fukushima Daiichi, where this plant went critical. It was knocked out because of an earthquake that caused the tsunami. So effects of ionizing radiation on cells, as we learned yesterday, the atoms, right, are building blocks of molecules. We have enough of the right molecules together, they create our tissues, right? Biological effects of radiation begin with ionizing our cells, just like you said, Steve. So we get radiation, it bombards our tissue. If it's strong enough energy, it can kick off an electron. That starts the dominoes falling down, right, in our body. We can also cause excitation of a cell without necessarily kicking off an electron. We can have what's called orbital displacement. So an electron jumps up to a different orbital. So if you think about like a target where you've got a center and then you've got a bunch of rings around that target, right, that we might shoot at or aim at. Think of an atom as having the nucleus at the center of the target. And then all those different circles around the target, those are different orbital shells. They have different energy levels. So electrons really like the nucleus. They love to be close to it. Just like my dogs now love to be close to us. How the hell are we going to go on vacation now with our dogs? Like after the pandemic, the dogs think now that we live at home every minute of the day. Anyway, so electrons like to be close to the nucleus. So it takes a lot of energy to remove them and get them to jump out farther and farther away. If you have enough energy from radiation, it kicks them right out. But you can just actually get them to jump out to a farther electron orbital layer, and that's called excitation. So we've got our cells, and again, these are made up of many molecules, made up of atoms. You can have a cell membrane, which is the outside of the cell, the cytoplasm, which is that nice gooey sticky stuff inside, which every other part moves in, And then we've got the nucleus of our cells, which have things like the mitochondria, RNA, DNA, that other real important stuff that helps our cells function. Cell sensitivity. So some of our cells are more affected by radiation than others. Ones that are more actively dividing are more sensitive. And ones that are less actively dividing can take a little bit more of a hit from radiation. So what would you say would be some actively dividing cells in our body?
I think it's your hair, right? That's why you lose hair when you get chemo.
Yep, yep, good. What else?
Would skin cells be one that actively skin cells?
What was that, Jesse? I couldn't
Right.
hear you.
Skin cells? I don't know, my computer's being weird again
Yes.
today.
Yes, skin cells. They're right. We lose skin constantly, and so they have to divide, multiply really quick, right, to replace it. Otherwise, we'd look pretty gross, right? What other cells in our body divide very quickly?
Your blood cells?
Yep, blood cells. Very good. Any others? There's a couple other big groups we could name. The lining of our stomach has hydrochloric acid in it. It's very, very strong. The only way our stomach could have that in there is if the cells that get constantly destroyed reproduce, right? So our stomach lining is constantly reinvigorating itself. Also, reproductive organs, sperm, ovaries. These things are very susceptible to radiation as well. With that said, radiation is also a teratogen. How would you define teratogen?
It causes something to mutate.
Yep, what specifically?
Fetus?
Yes, fetus, good to know. So teratogens are nasty. They are something that will affect the fetus as it's developing in the mother's womb. Less actively dividing cells are things like a brain and central nervous system tissues. Believe it or not, that gray matter doesn't replace itself, right? Which is why we want to keep all those neurons up here in good working order, because they don't replace easily. All right, good. Objective 3, identify the possible effects of radiation on cells. So there's 4 possible things that can happen. No damage, which is the one that I would root for. Cells can become damaged, but repair the damage that's caused, and they operate regularly. The cells get damaged, they don't repair, but they still can operate. I guess much like a car riding on a flat tire, right? It still operates. Well, I wouldn't call it normally, but it's still going down the road. And then cells die as a result of the damage. I'm sorry, cells can get damaged and operate abnormally. This is our cancer here, right? Or they're not functioning in the way that they're intended. So let's define the terms acute and chronic dose and state examples of chronic radiation dose. So what do you remember from our chemical exposure? It's the same thing. How would you define acute or chronic dose of a chemical to a worker?
Well, acute would be a strong dose, and then a chronic would be dose over a long period of time.
Right. So acute's usually a strong, high, concentrated, what have you, dose in a short period of time, and a chronic is usually low over a long period of time. Could be months to working lifetime, right? And with radiation, the potential biological effect depends on how much and how fast. So it's almost like the difference of flow through a pipe. So the larger pipe that can accommodate more flowing water, that's going to be cause more detrimental outcomes. So if you have a more active radiological source that can provide more energy to your body in a short period of time, like alpha radiation, that's going to be more detrimental. Define acute dose and give an example of for an IPAT member may face on a job. So you said what acute is. How about an example that you think one of our members might experience on a job?
The XRF gun we were talking about yesterday.
Good. Yep. Good. Any other examples? This here would sort of be an accident, but I just told you that 2 accidents happened recently within the last few years at Hanford, so these still happen. How about an IPA team member accidental release of radioactive coating of a substrate that was contaminated with radiological materials? And again, when they're doing this work at these legacy DOE sites, they really do go through a lot of control procedures. So they have to develop a radiation work permit or radiological work permit, a RWP. And it's basically like a job hazard analysis, but they, very detailed, and there's worker involvement. One of the accidents occurred, um, the first one that I worked for the local plumbers and steam fitters, because they were using these big foam cannons. So they were spraying down the demolition work area with this foam. Hanford is in the desert, but it also gets very cold there. And nobody checked whether or not that stuff would freeze. And so this accident occurred in the winter months. And what happened was the foam that was being delivered froze and it didn't work as intended. And so there was a exposure of radiological construction material as they were demoing it. So, that's something that didn't get caught at the time. So these
Right.
accidents can happen. Yeah.
So I guess it's safe to say we have some of our industrial members that do in-house work on a lot of nuclear plants. Could they potentially be exposed to some of this radiation
Yep.
during
Yep.
some of the procedures that they do there, like abatement procedures?
Absolutely. And, they should be getting a radiological worker, 2 training if they're going to be doing anything that could potentially disturb radiological material, which could be radiological contamination on coatings, right? Even if you're not going to remove it, but you're just applying a new coating over it, you still have to prep the surface. So you're going to be, by definition, disturbing that stuff. So that's got to be done. And,
I'm pretty sure they do training from the facility itself, but it would probably be better for us to ensure doing this training to our members so they'd be better prepared, because
yes,
they may or may not be giving them all the necessary information.
Exactly. And like I said, this, these 2 courses came out because I was asked by, 2 different unions to develop training for their own members that would be, more applicable to their members. And maybe, how could I say this nicely? Maybe give the straight rational of thinking that's current on protecting people, right? And other unions do the same thing, like Leuna, the laborers, they have their own training. The Teamsters have their own training for their members that work around that stuff. It's still the responsibility of the employer, absolutely. But, why not give it a once over from the union side of things, right? Yeah, good question, Uno. One of the things I'm going to do once I can, travel and meet face to face, I want to hook up with our international organizing department and see if they've got any data on different places like this that our members might work, right? Whether they work in a place that might be exposed to radiation, or how many of them do commercial painting versus industrial painting, things like that, so I can start to get a good idea of hazard and risk assessment of our members. This is the result, this table here of acute doses, and this is in our manual. So a chest x-ray typically has about 0.3 rem. So this would be 1, 2, 3. So this would be about 30 millirem. Average annual dose from cosmic radiation, we have these values here. But we start to see symptoms creep over after you get past 15 rem. And this is 5 rem here is the annual allowable dose under DOE. Which I think by current research shows it's too low. And then we start to see what some of these effects look like. No symptoms of illness, minor and temporary drop in counts of white blood cells and platelets in our body, up to 100 rem, possible acute radiation syndrome. 10% of exposed individuals at this level may have nausea, vomiting within 48 hours, and mild drop in blood counts. And then once we get up into these values here, we can start to see, fatalities arise. Sorry, I should probably give a disclaimer. Sorry for the graphic photos here, but this was a photo of a 26 Curie iridium 192 source. It was a little disc that was placed in the back pocket of this worker. This is day 1 after it was placed. So you can see an immediate burn. Day 3, and this is the cell necrosis or death. Necrosis means death of this worker's leg tissue after 10 days. This is 26 Curies. Remember back to that Brazil example that I gave? It was 1,300 plus Curies, right? That's a huge dose. But look at what this did. And this isn't a very big dose. So this stuff can be extremely dangerous if folks aren't using it under appropriate controls. Define chronic dose and give an example. So we already defined what chronic means. How about an example of a chronic dose that an IUPAT member might experience?
If someone were working at one of those power plants, and that could be something where maybe they weren't getting a lot, maybe they weren't working around it directly, but because they were indirectly working around it, they could get.
That's right. Yep. Any other examples? I'll present one that I think probably happens often, and not just to IUPAT members, but many building trades. Exposure to the sun, right? So if you're outdoors and if we don't have the right controls in place, either being able to work in shade or with sunscreen, long sleeves, things like that, you are at a risk if you're doing this over your lifetime for developing, skin cancer, from excessive days of low dose of radiation.
Should have thought of that one, especially in Florida here. It's a big issue.
Yeah, and again, it's like you don't have to be experiencing heat from the sun to be exposed to ultraviolet rays. A good example, last July, if anybody took the PCB awareness class with me, Wayne, and Jim last July, I took a day off because I had a deep sea fishing trip booked. I came back with a terrible sunburn, and my son had a terrible sunburn, which, by the way, I harbor guilt to this day, because it was overcast and cloudy and it was cool out there. And I have the sunscreen and I'm like, I better put this on because I know better. Next thing you know, we're motoring out to deep water and I forgot about it. And I came back the next day and oh my God, did I have a bad sunburn. But I was not hot. It was nice and cool out there and it was overcast sky.
I think the overcast can be worse, actually. The overcast is worse because it can actually, not just the heat, but that I've heard at least that the overcast, thin enough clouds will actually magnify the sun's rays. I don't know if that's true or not.
It depends. And the other thing, Jesse, is so one of the controls is being able to wear sunscreen or long sleeves and stuff, right? Wear a hat. I don't imagine it's very fun to do that in Orlando in the summer.
It's hard. You sweat off the sunscreen as fast as you put it on. Honestly, you do.
Right. And one of the issues is if you get the sunscreen that's tolerable to sweating, it's actually not good for heat stress, because we want to be able to,
because it keeps the heat in. Yeah.
Right, we want to be able to sweat. So it's a catch-22, but we got to figure out a way to protect our members' skin from UVC light or UVB light, because it's serious.
Hey, Bernie, it's actually a very big issue for our glazers, especially because it's the reflective surface.
Oh,
so
yeah.
they kind of get hit twice.
Right.
Yeah, good. Yeah, really good example. Yep. Yeah. And if you're working around black surfaces and stuff like that too, where it's that's more an issue of heat stress, but anything that's reflective. So, metallic, white, glass, if you use treated glass, anything that can reflect the sun. Yeah.
Yeah,
Good point.
Most of it is reflective, and the metals, most of them are reflective. Like when you drive through a big city and you see the sun reflected off the
Right.
buildings, it's
Right.
being right up on that.
Yeah. Yeah. Good example, Steve. Define the terms somatic effect and heritable. So somatic effects refer to the effects of radiation that an individual receives. So here, I'm getting the dose, I'm going to have the detrimental effect. There's prompt effects that happen for the most part immediately to, a few minutes or a couple days after, to delayed effects, which can take, many days or weeks to show. A heritable effect is something where, a mutation occurs and it's passed on to offspring. We haven't observed this in humans, and they have been studied from incidents like, Nagasaki and, Hiroshima. We've also had study from outfall from Chernobyl. We haven't observed it, to my knowledge, in humans, but we have observed it in plants and animals. So this makes me nervous. And this year I've got White Light, Black Rain, very troubling documentary to watch. If folks are interested in the health effects and the aftermath and things like that of these two bombs, but good documentary. Speaking of documentaries, there's one that I got to see about the IUPAT bridge painters. Gotta make note to self, have Anton send me that DVD.
Yeah, Bridge
Yeah.
Brothers.
Yeah, last I saw it was
Yes.
on it was Amazon Prime.
Really?
Yes,
That was about maybe 6 months ago, so it might still be there.
yes, it is.
Is it?
All right.
Yeah, it's Bridge Brothers. We actually use that in our lead class.
Okay, cool. I will put that on the list of things to watch this week. Thank you. All right, factors affecting biological damage from ionizing radiation exposure. So total dose, so the greater dose that you get, obviously greater potential for biological effects. This is going to carry into especially acute doses. Dose rate, again, how fast you get is going to be an issue as well. Type of radiation, like we covered yesterday, remember the radiation weighting factor that we have to apply to our Rankine value. It's going to be highest for alpha emitters. We had to multiply it by 20 for alpha emitters. Area of the body that receives a dose. So depending upon which part of the body is irradiated or subjected to the radiation, we have different exposure limits. And I'm not going to get into those too much because I would talk about that in a dosimetry course. But depending upon which parts of the body are irradiated, you are allowed to have larger or smaller doses cumulatively over a year. And they also have broken doses out into quarters. In fact, OSHA has a radiation standard. I think it's 1096. Doesn't apply to DOE workers. So, but it applies to any other site under OSHA. So they actually break out in quarters how much you can get for different parts of your body. The cell sensitivity, we mentioned, rapidly dividing cells are more sensitive, and then individual sensitivity. So we might have, underlying issues that might cause us to have greater effects from that radiation. State potential effects associated with prenatal radiation dose. So sensitivity of the fetus is an issue if you are thinking about becoming pregnant or you are pregnant and you're a DOE worker. There's a special procedure that you can go to declare yourself a pregnant worker, and then you fall into a separate set of protections. Embryo and fetal cells are very rapidly dividing, as you can imagine, right? So they are going to be very much susceptible to doses of ionizing radiation. The most susceptible time is 8 to 15 weeks after conception. And again, sometimes, you might not know when you're pregnant until it might be into that period where they're going to be most susceptible. So again, that declared worker pregnancy rule is an important part of protection for women in Department of Energy. But if you don't know, other protections might take a little bit longer to put in place. Other risk factors during pregnancy could also increase the likelihood of the severity of effects to the developing fetus. And then there are specialized dose limits, which will go along with a declared pregnant worker. Objective 7, compare the biological risk experienced by the general population from chronic radiation doses to risk experienced by healthcare workers who are subjected to radiation in their daily work. So it shouldn't just say healthcare workers. I apologize. It should say radiation workers. So this is, an issue of any amount of radiation can result in potential health effects, including cancer. As NIOSH and the CDC states, there are no safe levels of uptake from a carcinogen. So any, dose of that stuff into your body, whether it be ionizing radiation or a chemical, it's going to increase your risk to suffering, potential carcinogenic outcome from that dose of the chemical. And as the dose goes up, your risk goes up. So it's better to be safe than sorry. This is a life expectancy retraction table that you could expect to lose how many years or months off your life for certain high risk activities. This is put out for the DOE, and I'll be straight. They put these out to try to do a risk comparison, so workers can look at this and say, oh, okay, well, being a radiological worker isn't as harmful to me as smoking. So it's a way to kind of look at risk and try to make then a judgment for yourself if that's personally acceptable to you. So, an average smoker is going to lose 6 years off their life, overweight 2 years, alcohol use a year, agricultural accidents, and then we get down to occupational radiation dose of 1 rem a year, which is, even more. It's 10 times more than what the average DOE worker gets. They would expect to lose 51 days off of the course of their lifetime. So, this is an issue, especially if you work in the airline travel industry, because to my knowledge, there's no known way that I know of to make a leaded roof of a plane. But one transcontinental flight, you're going to get about 5 millirem a year. So, what does this mean? Imagine, being a flight attendant or a pilot, where you're constantly going back and forth, right? Why is it, do you think, that you get such a high dose when you take a flight?
It's the same reason we talked about the ozone. Like you're higher,
Yeah,
right?
right. Exactly. You are outside of that protective atmospheric barrier. So, and this is an issue. We have seen, cancer cluster increases, for flight attendants. There's been some study on this. Risk from exposure to occupational ionizing radiation. So this is the slide, if you're going to take the test, that you need to memorize, not the slide that comes after this. So what you need to say is that no increases in cancer rates have been observed at occupational levels. Possibility of cancer induction cannot be dismissed, however. So there's their disclaimer. Risk estimates have been derived from high levels of exposure to radiation. Like I said, our radiation models are based on the bombs dropping, Chernobyl, uncontrolled radiological work back in the 20s, 30s kind of thing, right? Now I'm going to show you the slide Bernie wants you to see, but don't use this one for your test if you ever take this test. So this is right out of this Richardson study that came out in 2015. Contrary to the belief that high dose rates exposures are substantially more dangerous than low dose rate exposures, the risk per unit of radiation dose for cancer among radiation workers was similar to estimates derived from the studies of Japanese atomic bomb survivors. What do you think this means? Digest that statement for a minute and take a gander at what you think that means.
So like long-term exposures, like equal to living through an atomic blast. Is that what it's?
Ding, 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 ding. You got it. I have no prizes, Steve, other than my generic bell ringing there. Very good. So like I said, the DOE and other radiation protection agencies have based the harm on these few incidents throughout history of very high acute exposures And they said, okay, we know if it happens at this level, we'll just draw a line backwards. So if I draw this regression line backwards, it kind of shows here at these low exposure dose rates that you're probably not going to have any health effects. That has turned out not to be true. So statistics shows us that the more people we have involved in a study, the closer it is to probably a true value, right, or a true outcome. So this study was derived from over 300,000 nuclear industry workers from France, the UK, and the US. That is a humongous number of people. And they followed them through their careers. So if you multiply the number of workers by their career years, you get a huge person year total for a study. It's large, very good for statistical validity, very good for statistical weight. From that, what they saw was that of the almost 67,000 known deaths of those workers, almost 18,000 of those deaths were due to solid cancers. So non-leukemia stuff. So, tumors, things like that. What the outcome of the study basically says is, look, as your dose goes up, your risk goes up, and there is no known safe levels. You can look up this report. You Google this, you'll find it. It's pretty solid. It's pretty solid science. And this is the. Go ahead.
How do those numbers work out compared to other forms of employment? I'm just thinking like we just went through every contributing factor that could cause radiation exposure. So like a nuclear industrial worker that smokes for 40 years, like you know what I mean? Like,
yeah,
or he has high radon in his basement or something, you know what I mean?
Yep. So there's going to be an increased contribution to that. So the study does say that there are a couple of shortcomings, and one of those, they list two for confounding factors. So confounding factor is something that's going to kind of nudge the data in a direction that you weren't looking to go, whether it be positive or negative. So a confounding factor can take away from your end result, or it could add to your end result. And two of them are smoking was one of them, and the other was asbestos worker. Because you'd imagine the amount of asbestos in these old 1920s, 1950s buildings, right? So those are two confounding factors that they did attribute in there, but you can adjust for that in your study.
Which I'm sure silica will probably fit into that category. So.
Yeah, right. Yep. Yeah, I remember one time my plane had to circle around for like an hour because they had a dust storm, a sandstorm at Hanford. And when I went to the training center at the Hammer Training Institute, there was sand on the inside of the windowsills. And I'm like, where'd this come from? They're like, oh, that was from our sandstorm we just had. I'm like, what the hell? I thought these are sealed windows. They don't even open. How did that happen? They say dust gets everywhere when they have those sandstorms. And when they have wildland fires, it makes it worse because there's nothing to control the dust. So what is that stuff full of? Crystalline silica. Yeah, good point, Nuno. So the take home from this is the current, look, it's the same way though. Like if you look at our chemical exposures, right? We had permissible exposure limits that were redone and vacated in 1987. Went through the courts, industry was able to say, hey, you didn't show that these are any more protective than the old ones. And the Supreme Court sided with them. So we have these outdated chemical exposures as well. And we have an outdated radiological exposure limit as well. It's not fair to workers. We have better science. Can we please just use it? Lifetime dose and health risk to a worker, who has been internally contaminated with radiological material is complex for many factors. So it's really difficult to go through the toxicological profiles when somebody gets these materials inside their body, because you're dealing with two things. And unfortunately, what the health physicists say are, well, the radiation dose internally is not going to be that much and blah, blah, blah. Well, great. But how about the damn toxicity issues that you're going to have because you just, took in heavy metals inside your body? Almost all the radioisotopes that we're talking about are heavy metals. And we know those aren't good, right? Does anybody here think lead's good or cadmium's good, right? We have all these classes around this. So there's two issues. You've got, the physical property itself, and you've got a radiological property of that chemical, but you also got the toxic properties of that chemical. Both bad. The size of the material that you might have been exposed to, and where did that end up? The exposure route, was it ingested? Was it inhaled? And then the radiation dose and toxic effects, these two things have to be considered together for the well-being of that worker. You can't just look at, and some days when we're able to get together, and if the topics of conversation are so boring, I have to bring up radiological dosimetry of workers at Hanford sites. I can do so over some beers or margaritas. And you'll see these things are really complex and they're crazy because when they look at workers who were internally contaminated with this stuff, it's hard to my mind that they actually get justice. With that said, time for an activity. So all of you should have your books. This here is the recent sheet out of EPA. I'm sorry, out of the NRC. Oh, let me go back. Out of the NRC. There's also a fillable online one that you can use too on the EPA. But basically what I'd like folks to do is we're going to take 10 minutes, go through and fill this out, and let's see what our annual radiation dose is in millirems. So I'll set a clock for 10 minutes. If you want to use this time too, go grab a drink, hit the restroom, etc. Feel free to do so. So I'll see you at 10 o'clock. What am I talking about? I'll see you at 2:40. So we can see some of the stuff that we, were asked to enter here. Cosmic radiation at sea level, and then depending upon, where you lived, you had to add, a factor to that. Terrestrial from the ground, depending upon where you lived. House construction, if you lived in stone, brick, or concrete building. Internal radiation was a fixed value. Weapons test fallout, we all get to add something for that. Jet plane travel, so for each 1,000 miles you travel, add 1. So if you do a lot of flying, you can see that could add up quite quickly. Porcelain crowns or false teeth, gas lantern mantles when camping. Remember I mentioned those yesterday. I actually didn't think that they produce those anymore, but I guess I'm wrong. If you wear a luminous wristwatch, luggage inspection at airports. If you watch TV, I'll be adding a lot for that over the last year. If we use video display terminals, same thing, right? Smoke detectors, that has an alpha source in the detectors. If you wear a plutonium powered cardiac pacemaker. If you have medical exposures, and they list a bunch of different ones there that you could choose. If you live within 50 miles of a nuke plant or within 50 miles of a coal-fired electrical utility plant, and then you can come up with your total REM dose.
I had a question on that.
Anybody want to share what they got?
I had a question actually. So one of the questions was if you live in a state that's bordered by the Gulf or the Atlantic coast, do I double that since I'm bordered by both? In Florida here?
Good question. Let's see.
I know that Florida's
No.
yeah, okay. I know that Florida's the only state that's bordered by both the Atlantic and the Gulf, but yeah. So
Boy, Jesse, that's some good trivia. I'm gonna have to remember that. So did anybody get above what the average annual dose is?
I'm at 333.
333,
I was at 364.
364,
I was 340 and change.
340, okay. It's all right around, seems the average. I would imagine that some of our ATRs might be up fairly high if they fly, right? And have to tack on a bunch of ones due to plane flights. Every time I jump down to Orlando, I have to add one, right? And every time I come
Right.
home, I add another one.
I had a good number of points added there.
Yeah. All right. So again, this is something interesting that we can do. It's a nice activity, if you're teaching, a class like this and you want to cover radiation, ionizing radiation of any level. It's a good way to kind of put things in perspective. All right, moving on. If we had any site-specific info, if we were working, on a Department of Energy site, DoD site, things like that, we could add that stuff in as part of our radiological control program that we'd be working towards for an activity. But with that said, let's do an activity now. So we've got that activity at the end of the student manual. And Nicole, if you could put them in a breakout room, please, for 15 minutes all together. Go ahead and do it as a small group activity. Look those things up together, discuss them, and then we'll come back. We'll just debrief it, see if we've got any questions, and that'll call it a day for our course today. Sound good, Nicole?
Yes, but my breakout room thing is acting crazy. So sorry about that, y'all, but see you in 15.
Okay.
Just because I needed to take a picture to show my boss or whatever. So I do have a few. I'll definitely send them to you.
Okay, cool. I promise I will delete them immediately. After
It's okay. Yeah, just don't, post them online and be like, look who.
I don't even know you. I don't even know this person. Who's this
Yep.
crazy person?
That's right.
All right, I better debrief these because I'll talk to you about this all day. All right, folks, so I apologize. The first question, for some reason, the definitions got deleted, but did anybody just look up the definitions to somatic cell sensitivity, DNA, and genetic effects?
I think we have them.
Yeah.
Somatic effects, a delayed effect. Cell sensitivity is how fast a cell divides. The DNA, there was a lot for DNA, but it's essentially the blueprint for your cell.
Yes. Yep.
And then the genetic effect is something that's passed on, like.
Right.
Yeah.
Right. And so for somatic effects, that's what happens to us as the person, and it can be delayed or immediate, right?
Okay.
Good. How about number 2? Which one of these would you say are acute and which ones would you say are chronic?
We had a good debate about this. Like,
Some could be a gray area.
Yeah. Okay. All right.
Yeah. So we got acute for vomiting.
Yep.
Leukemia, chronic.
Yep.
This was one of the debate ones, hair loss. I mean, for the most part, I think it says on here acute.
Yep.
But it could be something that is chronic as well, no, depending on the exposure levels.
Yeah, I mean, if the hair, if the hair rejuvenation follicles got damaged by radiation, then that would be, yeah, right. That's something that doesn't repair itself. But for the most part, it's acute.
Okay.
And how about skin?
Acute.
Yep. And how about the low red blood cell count?
Chronic.
Yep. Good. And again, that's one too, that if you get, hit with it, if you could detect it, right? If you happen to detect it at the time, it could be something associated with acute, but it would come right back. If you've got a suppressed red blood cell count consistently, that's a chronic issue. What are the 4 main types of natural radiation?
Cosmic, terrestrial, internal, and radon.
Good. And how would you select these as being either natural or man-made? What would you say for these ones? Radon would be what?
Natural.
Yep.
X-rays, man-made.
Yep.
Nuclear fallout, man-made.
Yep.
Carbon-14, natural.
Yep.
And bananas, natural.
Yep. Indicate the average annual dose the general population receives from the following.
Cosmic, we have 28 millirems a year.
Yep.
Terrestrial was also 28. Radon, we had 200.
Yep.
And then medical X-rays, we had a discussion about this because the medical field was 300, but it was broken down and we couldn't find anything that specifically said X-ray, but
Good.
it said 40 on that sheet that we had.
Yep.
So
Yes. So based on those figures that are in the manual from the DOE, so the one in the middle, medical, I can't remember what the phrase is in the middle, but that's basically like medical pharmaceuticals and things like that. So the first category is the tomography and the X-rays at the bottom. Those are two different styles of X-rays. So if you add those together, you get about 225.
Huh.
Which number are we on here? All right, how about estimate the sensitivity levels of cells of the following body tissues, high, moderate, or low?
brain, we had low. Hair follicles, we had high. Bone marrow, we also had high.
Yeah.
Skin, we had high. And then stomach lining, we had high.
Yep. I wouldn't have selected moderate for any of those. Good. How about 7? If you are a radiological worker, showed an effect from exposure to radiation, what type of an effect would this be?
Somatic.
Somatic. Good. If your child or grandchild showed an effect from radiation dose that you as a radiological worker received prior to conception, what type would that be?
Heritable.
Good. And lastly, what are the 3 potential effects from prenatal exposure?
Birth weight, smaller head size, and more incidences of mental retardation.
Good. Excellent. All right. Let's see. Where did my thing back here? All right, last slide. Comments or questions? Gotta be the theatric.
Well, everybody knows that.
All right, what is it?
It's 3, and I know his name too. Do you remember the fish's name?
What's the name of the fish?
Blinky.
Yes, very good. Very good. That's it. Very good, sir. All right, everybody, thanks. That does it. Congratulations. I'll give you a slow clap. You made it through both fundamentals of radiological materials and health effects of ionizing radiations. Very good. And everybody did well. You had some good contributions to the course, and I've got no doubt, if you were to take the DOE test, you'd do just fine. Anything we can discuss before we sign off?
I wanted to make a quick comment. That something that kept popping in my head this entire course was, I don't know if did you ever watch Chernobyl when it was on HBO?
Yeah, me too. I've seen
No, but I have access to it.
Well, definitely watch it because
it's hard to watch, but it's good.
Yeah, it is tough it's kind of very scary.
Okay.
But it goes into a lot of the stuff you talked about.
Yeah, they do. It's really well researched and well done. But it's really crazy.
It's a bit depressing if you can handle it.
Especially just the sheer amount of denial that the scientists were in when it happened. Just absolute denial. It's crazy. The one scientist was literally suffering from acute radiation poisoning, and you just nah, it didn't happen. Everything's fine. What are you talking about? It's nuts.
Man, that's crazy. That parallels some of the verbiage I hear people today say who are dying of COVID. Their last breath, they're like, no, it's not COVID. It's something else.
Right. It's so true.
Man, I don't know how people get like that. I mean, I know Russia obviously, ruled with an iron fist, right? I don't know if the documentary talks about that at all, but so is it like a docudrama or a documentary?
I guess it's kind of a docudrama because it's dramatized, but they do also. I don't remember if they actually go in and talk, or if I just happen to watch a documentary, like a regular documentary, at the same time because I was so interested in it.
All right, I'll check that out this weekend. They
definitely go into the politics of Russia and stuff, and how that affects everything.
Well, during Fukushima Daiichi, it was so bad over there. The workers knew it, so they needed people to go in and try to fight the meltdown. And folks who are, in their late 50s and 60s with no family, they were volunteering to go in and do the work because they
Right.
knew they were going to die. I mean, that's scary.
It is.
Crazy.
Another thing that made me think of Nova not long ago had an episode about them trying to recap the Chernobyl, them trying to redo a new ceiling or whatever to cap it because
Yeah.
it just the thing that was put in place is not meant to be long-term fix. So there's a whole episode of Nova about it, about how they're constructing it, just what all the effects were and why they need to do this new thing. It was really fascinating, so I recommend it too.
Yeah, the problem is that's there forever. Certainly our
Right.
lifetimes and our great
yeah.
great great grandchildren's lifetimes.
It's been long enough that the fixes they put in place at the time are not going to last much longer, and they need a better fix.
Right. And that's one of the issues that some technologies like this, like ideally, is nuclear power clean? Yes, it is. But the problem is it creates waste which we can't handle, and it's prone to accident because we're human beings. And so the outcomes of those accidents are so detrimental, they outweigh the benefits that we could have. So it's
Right.
tricky. That's why, you know, science and technology on one hand gives us some good stuff, but it also creates a lot of bad problems on the other side, and they don't seem to always equal out. Man, well, thanks everybody. I enjoyed these two
Thank you.
courses.
Oh, there we go.
Okay.
Okay, all right. Yeah, we've got Amazon Prime, so which, by the way, I have to send a nasty letter to Bezos off because do you see what they're doing to those